All right, so we want this area, which is the shaded region. To find that, let's take advantage of the symmetry and just find the part in quadrant 1, and then we'll double it. So we'll find that area, and we'll double it. So how to do that? You'll want to draw a picture of the radial arm that passes through the intersection point of the blue and the black graph, the first function and the second. All right, let's find the theta value where that happens. So we set them equal to each other. We'll isolate sine, and the angle measures where sine is 1/2 is pi over 6, and 5 pi over 6, and 13 pi over 6, and onward, but it's probably just going to be pi over 6. All right, so pi over 6. Let's just do a quick check. For the black curve, the R value, when you're pointing at 30 degrees in quadrant 1, is 3 times 1/2, or 1.5. So pointing in that direction, move 1.5. Looks about right. All right, we know the boundary. And now, will we be pointing up here when this radial arm sweeps up? Will that just be a good old pi over 2? Let's just do a quick check for this black curve. When theta is pi over 2, the radius, or the distance from the pole, will be 3 times 1, or 3, which is exactly what that point is. All right, so the black curve is definitely swept out by this radial arm from pi over 6 to pi over 2. Is the same thing happening for the blue curve? We should check before we just assume that it is. When theta is pi over 6, the blue curve is 1 plus 1/2, which is 1.5. Yep. And when theta is pi over 2, R2 is equal to 1 plus 1, which is 2. Beautiful. So to find the yellow region, we know that our rotations go from pi over 6 to pi over 2. All right, let's set up our integrals. So to get that region inside the black curve but outside the blue curve, which is in yellow here, we need to do this entire region, which is basically the radial arm sweeping on the black curve all the way from pi over 6 to pi over 2, minus this green region, which is the radial wave sweeping this space just between the blue curve and the pole. When we subtract that, we'll be left with exactly what we needed. And remember, they're asking for the entire, that's like moon shape. So we're going to have to find that and then double it. All right. So this difference will represent this area minus that area, which will be that area. And so our final answer that represents exactly what they asked for will be 2 of those. And then you should be able to enter that into your calculator and get an answer. So if you do that on your calculator says about 3.14159, blah, blah. Wow, the answer happens to be exactly pi, which you might have gotten if you'd actually evaluated this analytically. But with the calculator, we get 3.14159. All right, I hope that helped. Oh, and also keep in mind that since these limits of integration are exactly the same, we could write it as a single definite integral. We could factor out the 1/2. So 2 times 1/2 basically goes away. And then we have this r squared minus that r squared. So 9 sine squared minus 1 minus 2 sine of theta minus sine squared. So we'd have 8 sine squared. We could bring the 8 in front. So it's just the integral of sine squared. And onward and so on. But it actually is not an easy definite integral to do using trig identities. So we are just sticking with our calculators for now until we review the AB curriculum, and that was our answer.